Okay, we're going to be going over 2.3, operations with sets. Okay, so I'm going to show you several different illustrations, and then we'll go into Hops and do several examples. So first, I want to show you what a Venn diagram is. Okay. Usually what a Venn diagram is we just draw this box, which we call our sample space, okay, or it might be also known as the universal set. So you might see a U in this box. That U stands for universal set. And what that means is the set that contains everything. Okay? So everything, when we see this, is the set that contains everything. So we're going to be using these Venn diagrams to show you what these set operations are. Okay, so you'll just see a box, you'll see a U, which represents everything that we're describing in the problem that we'll be working with. Okay, so one of the first ones we look at is intersection. Okay, intersection is also used when we see the word and. If you see and, it's also referring to intersection. The symbol that you'll see is this upside down U shape, no tail on it. It's like an upside down U. So intersection, keyword is and, upside down U symbol. And here's the Venn diagram for what that looks like. So we're going to talk about A, which just represents some set, intersect B. Okay, otherwise A and B. Okay, so what does that look like? We have one circle that's going to represent the set A. We have another circle that represents the set B. The intersection is just the part where they overlap. So it'd be this part right here in the middle. Okay, so that's what A intersect B means, where they overlap, where they intersect. Okay, next to it I'm going to talk about union. Keyword for union is or. So sometimes you might see or. The symbol for union is just the U shape, no tail. Okay, so this U shape. Now, I know you guys are familiar with the English language, and when we say or, we either mean this or that. Okay, so I can say, do you want chocolate or vanilla? Okay, not both. In this case, or could mean both. Okay, so you might want to write that somewhere. Or, in this case, in this setting, could also mean both. So somebody said, do you want ice cream or cake? Yes would be a simple answer, because there is such a thing as ice cream cake. Okay, so you can get both. Here's what union is. So it might say A union B. This is asking for all of the elements that are in A or B or both. Okay? So here's another Venn diagram. Here's A. Here's B. When we talk about the union, we would do all of A. And then we would also do all of B. So A union B would be everything, all of A and B, okay, and the intersection. Now later on this will be important, but I'm going to go ahead and talk about it now. There's a formula for A union B. A union B equals this formula. It equals A plus the elements in B minus the elements in A intersect B. I think the book uses the cardinal number, but we'll talk about this. So why is this? Because A union B, you guys can understand it means A plus B. But why do we have this minus A intersect B? So I'm talking about that. Here's the way you want to think about this. I got this diagram. And you will see it more in word problems, but I'll just try to show you the illustration here. Whenever we do A union B, we count everything that's in A. Okay, so I'm going to do vertical lines just to highlight A. So this part that goes over in B, this is also A. Okay. So when I count A, I counted this portion right here. All right. Then when I count B, and this is why I did it, the lines differently, B will be all of this part, right? But guess what? This part right here that overlaps again, I'm counting this piece twice. Okay, so sometimes you might get a survey and they might say, well, 10 people wanted this and 15 people wanted this, but there were only 20 people in the room. So if you add up 15 and 10, you get 25. So it's like, how do you get 25 and there's only 20 people? Well, what they're not telling you is that this part was counted twice. So when we count A, we counted this part once, okay? I'm putting the number 1 here. And this part was counted once. When I count B, this part was counted once, but I also counted this part again. So notice, this middle part got counted twice. So in order to fix that, we have to subtract it off one time. And so that's why this is part of that formula. So this is good to have. Okay, so now we're going to talk about disjoint sets. Okay, so these are sets that have nothing in common. We know sets are disjoints if this is true. You might see A intersect B. If you know that when you intersect these two things, you get the empty set. Okay. If this is true, then these are disjoint. Here's what it looks like. You would have circle A, which is completely separate from circle B. They have nothing in common. Okay, so these are disjoint. Okay. So sometimes they overlap, sometimes they don't. There's a couple more I want to talk about. Complement. Complement is denoted by, let's just say, I'm going to use the set A. You might see a little apostrophe. You might see vertical bar. You might see a little C. Okay. I'm probably going to be using this apostrophe here. Complement means everything except that element. Okay, here's a Venn diagram that shows you what complement looks like. So we're going to be talking about A complement. So here's the set A right here. If I want to talk about A complement, that means I want everything except A. So I'm not going to shade inside of A, I'm going to shade on the outside of A. So everything within the universal set in the box except for A. So this is A complement. And then we'll see some mixtures. Okay. So some of the things we might see A complement union B, and we might see vice versa. So I'm just kind of noting those, and we'll just work them out in the problem context. But I'll show you some of the Morgan's laws, because we'll start mixing them up. You might see, you know, A complement intersect B. They'll just start doing a whole number of these. So you might, complement might be before, might be after. Sometimes they might even add a third one, which we'll see in context. But the Morgan's laws, I'm going to show you those, and then we'll jump into some examples. He just kind of gives us a shortcut with some of these complements. So one of them is A complement union B complement. So if you have this going on, there's an easier way to do this. He found out, the way I think about it is, think about this complement kind of like a -1. -1 does the opposite, or it changes things from positive to negative. So if you were to factor out that -1 or that complement and put it on the outside, everything inside would change. So this would now be positive A, no complement on it. This union would get flipped to the intersection, and then this would now be positive. So this is one of the Morgan's laws. It just takes that complement out of everything, puts it on the outside, and if you just do A intersect B, the opposite of that, the Venn diagram that you get, I think it's much easier to go through this than this, and I can show you both. But A intersect B, okay. This is A, this is B. A intersect B is right here in the middle. Talked about that. But we want the complement of A intersect B, so we want everything except for this part. So that means we're going to be shading the whole box, everything except for this piece. Everything but the intersection. Okay. And it's much easier to see by doing this versus doing this. Because A complement, you have to shade everything but A. And then B complement, you would shade everything but B. And then you have to add together the pieces that had double shading, which would be all of this. Or add together the pieces that had any shading. And then there's one more. That is A complement intersect B complement. So you can probably guess if you just factor out or kind of translate that complement outside of the parentheses, we would end up with A union B, and then the complement will be on the outside. So A and B, okay, A or B, sorry, the opposite of A or B. Okay, so here's what that Venn diagram looks like. Call this A, call this B. A or B would be everything, all of this. The complement of A or B would just be the outside, okay, not including any parts of A or B. Everything outside of A and B. Okay, so these are the highlights of the section. Now we'll just practice some of it in Hawk.